Good morning, mathematicians. Was this a little, and maybe that's better, I don't know. Brower groups. We're on to Brower groups today. Good for us. Morning, mathematicians. Was this a little... I wonder what other streamers do to get their systems set up properly so that they don't do all of this weird stuff on stream. I don't think I really care enough to do anything different. I think it's fine. But obviously other people are doing things differently. And that is a-okay. Good morning, Arad. Oh, interesting. I don't think I noticed until now, but Milne speaks in the first person in these notes. That's very interesting. Or is that maybe an inconsistency? I don't remember what he did earlier. I'm a big we person. I'm writing, my my next paper. It's me. I wrote it. I'm the author, but it's all we. I don't know. I like that about math. We're doing this together. The reader, the writer, across time, across distance. Anywho. Okay. Big Hamosh energy, exactly, yeah. Besides classifying... my brain is already malfunctioning. Or hasn't started functioning yet. What are Brower groups? Well, great question. You came to the right live stream because we're going to find out together today. Actually, I kind of know what they are already, but that's what we're reading about today. Well, one thing is it defines a concrete interpretation of this cohomology group, but don't you worry, there's other, in my opinion, more down-to-earth descriptions, but depends on your perspective. Besides classifying the class field theory, Brower groups have many applications, for example, to the representation theory of finite groups, and to the classification of semi-simple algebraic groups over non-algebraically closed fields. Oh. All great questions have the same great answer, cohomology. Amen, Arad, amen. Throughout the chapter, K will be a field, all vector spaces will be finite dimensional, k-algebras. Okay. Modules, faithful modules, simple modules. Okay, standard stuff. Filtration. This is just some general algebra. The following conditions are equivalent. Let V be simple. What is this? What is this proposition? Be a semi-simple module. Okay. Yeah. What do you want to eat for dinner? Cohomology. We have cohomology at home. The cohomology at home. And then what is it? What's the fake cohomology at home that sucks? Okay, maybe I should read some of this notation. What is AA here? A acting on itself as a module, I assume? As a left module? Yeah, surely that's what it is. Okay. A k-algebra is said to be simple if it contains no proper two-sided ideals other than 0. The kernel of a homomorphism of k-algebras is an ideal in A not containing 1. Therefore, if A is simple, F is injective. Okay. Division algebra, Schofield. Okay. Right, and I got tricked by this again before because I saw D modules and I got excited. I should have known. I mean, we'll probably want to come back to these examples, but... Oh, the double centralizer theorem. This is interesting. Let A be a k-algebra, and let V be a faithful semi-simple A module. Then the centralizer of the centralizer is A. That is interesting. It follows from this lemma, apparently. For any V1 through Vn and B in B, there exists an A in A. And B meaning the centralizer of the centralizer of A. So we'll prove this in the case V equals 1. Note that AV1 is a submodule of V. And so there exists a submodule such that this is true. What the heck is going on here, Mapping Wild? Well, we are deep into a series where I read a book about Galois cohomology and class field theory. Here, right now, though, we're just reading about... Essentially, this is linear algebra. This is basically just dressed up linear algebra at the moment. It has to do with the theory of modules over a ring. But a very special kind of ring called an algebra. That's what this thing A is. You know, think like the collection of n by n matrices with addition and multiplication. So more or less, we're just diving into that. But we're going to soon talk about something really cool called Brouwer groups. Okay, so AV1 is a submodule of V. This should be true. Okay. Yeah, I guess that's just from 1.5, some algebra. Let pi be the map that projects onto here. It is alinear, and hence it lies in D. Really? Wait, how does this map? It lies in D just because it's alinear? Or I guess you got to do the calculation. Oh, I see. Yes, right. The alinearity... Right, the alinearity does mean it's in D because it goes before or after. Okay. And it has a property that pi v is equal to v if and only if v is in here. So now pi bv1 is equal to bv1, so bv1 must be in here. I see. Okay. So now we suppose that W is the direct sum of n copies of V. This again should be semi-simple. The centralizer of A consists of matrices such that such that this holds what for every entry of the matrix, basically. I see. In other words, the centralizer of A is MND. An argument as in this example. Okay, so I guess we'll just believe it. Okay. I'm willing to just believe the end of that proof. Where are the damn Brouwer groups? We're supposed to be reading about Brouwer groups today. Okay, whatever. Schur's lemma, very important lemma, endomorphism algebra of a simple A module is a division algebra. Every simple k-algebra is isomorphic to this for some n and some division algebra D. Every simple k-algebra is isomorphic to, I see. That's kind of interesting. So we choose a simple A module S. For example, any minimal left ideal of A. Then A acts faithfully on S because the kernel will be a two-sided ideal of A not containing 1, and hence it is 0. Right, so this is for simple A modules, I see. Or algebras. Let D be the centralizer of A in the K-algebra. According to the double centralizer theorem, the centralizer of D in here is A. So, wait. The centralizer of D in here is A. Why do we get the second thing, though? A is the D endomorphisms of S. Right. Hang on, I'm doing too much in my head. I gotta write some stuff out. Okay. So we have A. We've got some module here, and let D be the centralizer of A in the endomorphism algebra. So D is the centralizer of A in the endomorphism algebra. And then A should be the centralizer of D also in the endomorphism algebra. And so the claim is that A is the D endomorphisms of S, right? A should be the D endomorphisms of S. Well, if we take an A in here, it centralizes D as an S endomorphism. So we have this, right? But I guess, right. And I guess this D acts on S. Because everything is an S endomorphism, so you can apply D as DS. And so since these commute, that means A intertwines this action. Okay. I knew that's what it was going to work out to be, but I just, sometimes this early in the morning, you just got to write things down. Actually, you should write things down always. I should have been doing way more writing this whole time. Tell you a joke. Do I have any jokes? I don't think I have any jokes. I don't think I have any jokes. I don't know. Knock knock. No, don't even say who's there. I don't have anything. You've always been slightly repelled by this part of algebra. You could never grasp a good intuition for it. I don't know if I would say I have a good intuition for it, but I'm certainly not repelled by it. I mean, I think I went into this the other day, but I'm very intrigued by Merida theory and this question of understanding the group of autoequivalences of module categories. I don't know why. I just think it's an interesting question. Yeah. So I've spent some time reading that. The abstract cohomological definition is much more appealing to you somehow. Interesting. Well, maybe we can put our minds together and solve all of Brouwer group theory together. Okay, where are we here? I know you both said who's there, but I have nothing. I have nothing for you. I'm sorry. Who's there? It's me, the guy who doesn't have any jokes. Hey there, new to the channel. Welcome. How often do I stream? Every single day of the week, except when I don't, which is sometimes. But generally, I stream like every single day of the week. And well, historically, so all my streams are posted on my channel, so you can go back and see all that's happened before. They in the past were just office hours where I just talked about random stuff and people asked me random questions. But more recently, I've been trying to work through Milne's notes on class field theory. So that's what we're doing. Okay, so in Schur's lemma tells us that D is a division algebra, which is what we wanted. Therefore, S is a free D module. Oh. Is that just, damn, we really got to go back and read chapter 1. Got to have some math jokes loaded. Yeah, I should. I don't. Oh, wait, this was from this example. We should have just read the example. K-algebra is division algebra if every element has an inverse. Oh, okay. I guess maybe it's believable. Finally generated module over division algebra has a basis. Oh, okay. Oh, yeah, because I guess, I mean, if we're, well, no. Oh, if we're a division algebra, we're a PID, right? Yeah, but 6 afraid of 7, come on. I mean, that's not, I don't know. Everyone knows that. No one wants to, it's not a real joke. Because it's a prime larger than 5, yeah. Those also terrify me. Okay. Anywho, S has to be isomorphic to this, so end ds has to be isomorphic to mn d op. Oh, that's interesting. Why do we pick up the opposite there? Why do we pick up the opposite? I guess that's explained here. Oh, yeah. I guess it's something about, right, the homomorphisms and you can, like, have a map on itself by, like, right multiplication or something. So it switches the side of the module. Right, yeah. So we see here right multiplication is a linear endomorphism. And everyone is of this form. Right, and so the composition should give us this, but right, it's the right action, so we take the op to go there. Okay. Okie dokie. I don't know why I decided to scroll. I know what page number I was on. Oh, hell yeah, here we are. We're finally getting to Brouwer groups. Oh, hell yeah. Almost. I guess we got a little bit more to see on this page. There's also an interesting looking theory for Brouwer groups of schemes, but even geometrically, not so sure how to think about them. Ooh, interesting. Where were we here? Oh yeah, we were finishing up that classification. Okay. Modules over simple k-algebras. Let A be a k-algebra. The submodules of A are left ideals. The simple submodules are the minimal left ideals. And then the claim is that simple k-algebras are semi-simple. Of course. Why would you put the word semi there if you didn't mean it? Let A be a simple k-algebra. It suffices to show that this module is semi-simple. After theorem 117, we can assume that it's of this form for division algebra. And we saw in 111, again, we were bad. We skipped that. That the sets Li are minimal left ideals, and that this is true. Okay, let's go back and look at the ones. I shouldn't have skipped all these. I thought I knew everything. I think this took us to the wrong one, though, didn't it? Weren't we supposed to go to 111? Example 111. So sets of the form Li, where I is a subset of this, and Li is the set of matrices whose jth column is 0 for j not in I, are left ideals. Okay. Moreover, each L for a singleton is a minimal ideal. I've never heard that or considered that before. Right, but now I see why it's this direct sum. And those are simple. So that shows that that is semi-simple. Cool. Let A be a semi-simple k-algebra. Then the following conditions on A are equivalent. Actually, I knew I also should have read isotypic, because I was like, I know what isotypic components are. But clearly this is being used in a slightly different fashion. I don't think we're actually going to get to the Brouwer group today. What? 1 of 3? How is this 1 of 3? Okay. It needed a second. A module is said to be isotypic if it is the direct sum of a bunch of copies of a simple module. Okay, probably could have guessed that or derived it from context, but why struggle when we have control F in our lives? The proof of the equivalence of A to B follows from proposition 1.9. Right. That's just that. And C obviously implies B. If any two simple A modules are isomorphic. Wait, what? Condition C, any two simple A has a unique simple? Really? Oh, well, I appreciate that work. I was just, was it just yesterday or the day before? I was talking about how when I first started university, I remember I used to put on Leonard Susskind's lectures on string theory, and I would fall asleep to the sound. He had a nice voice. So I'm very honored to be next in line for someone to be serving that role. But I find this actually very shocking. I mean, I guess this is probably a well-known basic statement about algebra. But a simple every simple A module has a unique every simple A algebra, K algebra has a unique simple. I guess that makes sense. Because of the splitting behavior we've seen. And I mean, another way you could prove it is like if it's rejected onto some, if it had a simple sub, then you could write it as a sum of that and some other component. But I don't know. It's just, I don't remember learning about this before. It's kind of surprising. Maybe I should get back to working on my singing career. At some point, I used to do songs on this channel, and then I stopped. Maybe I'll get back to it. at some point. Maybe I'll write some math music at some point. Okay. Finally, B implies C because if A is isotypic, so also is a direct sum of copies of A. And every A module is a quotient of a direct sum. And math jokes, that's true. I guess I got to work on my math jokes. I listen to a lot of comedians on YouTube. I guess I gotta, channel that into math jokes. I feel like at one point, many years ago, I was a meme lord. I was a dank meme lord. And I feel like my brain turned to making math memes, which is it's a different business than jokes. Yeah. So let's see, if the A module is isotypic, why would that imply C? I'm still confused about that. Because if A is isotypic, so is a direct sum of those copies. Oh, and then every A module is a quotient of a direct sum. Sorry, I see it now. And then that you're just summing the same thing a bunch of times, and it's got to be a quotient, so it's just literally going to be one of those factors. And all those factors are the same. Got it. Okay. Let A be a simple k-algebra. Any two minimal left ideals of A are isomorphic as A modules. And A is a direct sum of its minimal left ideals. Yeah, so of course we know that these are simple, and that follows from the previous statement. The second part was proved in 118, right, which we saw from those ideals Li. If A is a simple k-algebra and S is a simple A module, every A module is isomorphic to a direct sum of copies of S. So we don't even get non-trivial extensions, hey? Wow. Kind of boring. I thought we were here to do some homological algebra. Any two A modules having the same dimension over K are isomorphic. Right. Wow. So that's crazy. That's crazy. Yeah, simple k-algebras are too simple. I mean, it's basically, yeah. Hello, Matthias. Oh, Matthias, you asked yesterday about solving, right? I think it was you. You asked yesterday about solving these mod n questions. These, I mean, I realized this is basically cryptography. I mean, in some sense, solving this is basically what's called the discrete log problem. And this is like so hard that it's used for cryptographic purposes. So, yeah, I can't believe it didn't cross my mind yesterday. But yeah, the question you ask is like cryptographically hard. You once tried thinking about non-commutative algebras through algebraic geometry. What do you mean by that? It didn't really work, but your conclusion is that simple equals point, and hence semi-simple equals discrete. That makes sense. So modules versus sheaves over that should be very trivial. Yeah. 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 I am very interested I mean, yeah, like I said, I want to think about this question. So, in the case, there's this paper, we've talked about it before. I guess discrete log is when the exponent is the variable. That's true, actually. Oh, that's true. So maybe I'm wrong. Maybe I lied. Maybe this question's more solvable than I made it out to be. Maybe it is more solvable than I made it out to be. I do need to think about it more. In your introductory algebra course, you were talking about cryptography. In class, you solved the problem when k and phi m are relatively prime. You wanted to hear it from me. Or phi p. Yeah, I mean, well, that's the... I mean, yesterday I mentioned, what was it? Yesterday I mentioned Fermat's little theorem, but this is actually a special case of, what is it? A phi p, a phi m is 1 mod m, or what's the generalization? Something like, I mean, this would imply this. Is this right, though? Maybe I've written this slightly wrong. Yeah. But I was going to say, automorphisms of the category of R modules. For a commutative ring, this can be recovered as automorphisms of the ring, and I forget which one's the normal subgroup, and the Picard group. But the proof of this basically passes through, you basically take R modules and you're able to sort of reconstruct spec R from this, and then you use geometry to prove this. And so the question that is on my mind, of course, is what about when R is non-commutative? Can the same proof be extended? Well, no, sorry, the same proof can't be extended, but does the result hold? And I don't know, but I'm very fascinated about this. And this involves thinking about, thinking about these geometric things, these algebraic things geometrically. I know that this is already captured in some sense in terms of the classifying space, but no, I won't speculate. I have some other weird group theory speculations, but I have to think about them more before I speculate about them out loud. You believe studying categories of modules is one of the main approaches to non-commutative geometry. Yes. Yeah. But it's just, the things I've read about so far, from what I've been able to dig into from non-commutative geometry, don't seem totally aligned with the things I'm trying to think about. But, yeah. Maybe some crazy smart people think about it geometrically. Yeah. Well, I mean, you can sort of imagine... You should somehow imagine modules over an arbitrary ring as somehow being sheaves on some non-commutative space, right? That's supposed to be the idea. But yeah. Okay. I think we need to wrap up stream, so we're actually not gonna. Tomorrow we'll finally get to the Brouwer group. Let me just finish this last corollary here. Let me finish. the integer n in theorem 117 is uniquely determined by A, and D is uniquely determined up to isomorphism. Interesting. So we get these two things for any simple A module, and n is the dimension of S as a D vector space. So since any two A modules are isomorphic, this implies the statement. Wait, does it give us the full statement though? If A is isomorphic to this, D up is isomorphic to this. And n is the dimension of S as a D vector space. Since any two simple A modules are isomorphic, this implies the statement. Okay, hang on a second. So what if we had... we cook this up so that A is isomorphic to MDN. But now suppose that there was some other... It was also isomorphic to little m E for some division algebra. Well... Because this sort of presupposes I guess maybe the wording here should mean it doesn't depend on the choice of simple module S that you take. Which is definitely true because all those simple modules are isomorphic, but oh, I see. Wait, this is part of it. Okay, suppose A is isomorphic to this. Then it should follow that D op is isomorphic to the A endomorphisms of S for any simple A module. Why is that true? Why is that true? This is some Schur's lemma type thing, right? Right, so A is isomorphic to this. Take some simple S. The endomorphisms, I guess you understand roughly what it's saying. S is essentially unique. Yeah, end AS. But why is end AS isomorphic to D op? That's what I'm... I guess maybe this is just a previous theorem. Yeah, okay, maybe this is just a theorem that was... Okay, this is probably just a theorem that we skipped over, that if you take... That in the special case where you take a simple M and DS module, it just ends up being isomorphic to D op. I guess that's something that we can just work out explicitly. Sure. Okay. So I believe that. And N is the dimension of S as a D vector space. Yes. Yes. Ah, okay. And then I see. So I see what that forces the n to be unique. Because right. Right, and that forces all the okay, I see. It forces all the D's to be unique as well. Yeah, because it's always just isomorphic to this as the structure, and because all the S's are isomorphic, all the endomorphism algebras are isomorphic. Okay, cool. So that's where we will leave it. I guess we'll have to retitle the stream because we didn't really touch the Brouwer group today, but tomorrow we will. So until then, you have some tools to go prove some things about k-algebras, simple k-algebras anyways. Yeah, so QED.